Hello everyone. Today I'll discuss Chapter 3 Understanding Quadrilaterals. Here is an introduction. Let us see. You know that the paper is a model for a plane surface. When you join a number of points without lifting a pencil from the paper and without retracing any portion of the drawing other than single points, you get a plane curve. Try to recall different varieties of curves you have seen in the earlier classes. Match the following. Here there are 4 figures 1, 2, 3, 4, and here the type is simple closed curve, a closed curve that is not simple, simple curve that is not closed, and not a simple curve. Right? Suppose this one, number 1, it is simple curve that is not closed. It will be here. If we match this one, we'll get that it is a simple curve that is not closed. 1 matches with C. Right? And this one you see, right? It is not a simple curve. It is a here you see this one. This one you see. This is not a simple curve. Right? This is not a simple curve, but this is a non-simple curve. Why non-simple? If you take a point, this point, here you take this point. From this point you can go in 4 directions. 1, 2, 3, and 4. You can, that means there are more than 2 directions, therefore it is a non-simple curve or not a simple curve, right? Here see, this is a simple closed curve. This is simple and also closed curve. This one is simple closed curve, right? And this one is a closed curve that is not simple. It is a closed curve or it is not a simple. This is a closed curve that is not simple, right? Let's discuss, compare your matchings with those of friends. Do they agree? Now here see, there are polygons also. A closed here you see polygons. A simple closed curve made up of only line segment is called a polygon. Here you see curves that are polygons. This one, this one, this one, all are polygons. Curves that are not polygons, these are not polygons, but they are curves also because there are two endpoints here. These are not closed. They are not closed. A simple closed curve made up of only line segment is a polygon. But this one, and this one are all curves that are polygons, right? Now try to draw a few examples, few more examples and non-examples of for a polygon. Draw a rough figure of a polygon and identify its sides and vertices. Classification of polygons. We classify polygons according to the number of sides or vertices they have. You see number of sides or vertices. If there are 3 sides, that is triangle. Classification is triangle. This is sample figure, right? Classification of this is a polygon of 3 sides. Here number of sides is 4 or vertices is 4. Classification is quadrilateral and it has 4 sides 1, 2, 3, 4. Number here next one is classification is a pentagon, that means 5 sides 1, 2, 3, 4 and 5. Right? It is a polygon of 5 sides, that is pentagon. It is a polygon of 6 sides, that is hexagon. It is a polygon of 7 sides, that is heptagon. It is a polygon of 8 sides, that is octagon. And if it is 9 sides, it is nonagon. And if it has 10 sides, in decagon. These are different polygons, right? That means you classify polygons according to the number of sides. Triangle has 3 sides, quadrilateral has 4 sides, pentagon has 5 sides, hexagon 6 sides, heptagon 7 sides, octagon 8 sides, nonagon 9 sides, decagon 10 sides. And if there are n sides, that is n-gon, right? N-gon, right? Now diagonals. What is a diagonal? You see here. A diagonal is a line segment connecting two non-consecutive vertices of a polygon, like this. Here you see PR and SQ are diagonals of this rectangle. A diagonal is a line segment connecting two non-consecutive vertices of a polygon, right? Here also you see that AC AD, DB, EC, EB, all these are diagonals of this figure, right? All these are diagonals of this figure, right? Now you see, can you name the diagonals in each of the above figures? Figure 3.1. Is PQ a diagonal? What about LN? What about LN? You already know what we mean by interior and exterior of a closed curve. Here you see, interior has a boundary. Does the exterior has a boundary? No. This is the interior of the closed figure, and this is the exterior of the closed figure. Right? Does exterior have the boundary? No. Convex and concave polygons. Here some convex polygons and some concave polygons. Here you see, these are convex polygon and these are concave polygons. Can you find how these types of polygons differ from one another? Polygons that are convex have no portions of the diagonals in their exterior or any line segment joining any two different points in the interior of the polygon lies wholly in the interior of it. Is this true with concave polygons? Study the figures given. Then try to describe in your own words what you mean by convex polygon and what you mean by concave polygon. Give two rough sketches of each kind. Here you see, if we draw the diagonal, here you see, if we draw the diagonal, all the diagonals are inside the figures. That means it is convex polygon. Here say if we draw the diagonals here, all the diagonals are inside the figure. Therefore, this is convex polygon. If we draw the diagonals here, all the is known as convex polygon. Here, if we draw the diagonals, these are the diagonals. These are the various diagonals, and all the diagonals are inside the figure. That is, these are convex polygon. Here, these are different diagonals. These are the different diagonals. These are the different diagonals, and all the diagonals are lie inside this figure. Therefore, these are known as convex polygon. Here in this case, you see, if you draw the diagonals, this diagonal is inside the figure, but this diagonal is outside the figure. Therefore, it is known as concave polygons. Here you see, this diagonal is outside the figure. This diagonal is outside the figure, but this diagonal and this diagonal inside the figure, but this diagonal outside the figure. Therefore, it is known as concave polygons. Here you see, this polygon is outside the figure. Therefore, it is known as a concave polygons. Here you see, this diagonal is in the outside of the figure, exterior of the figure. Therefore, it is known as a concave polygons. That is the difference. Here, all the diagonals are inside the figure, and here all the diagonals are not inside the figures, that is in the exterior of the figure. That is known as concave polygons, and this is known as convex polygons, right? Now, regular and irregular polygons. Now read about regular and irregular polygons. A regular polygon is both equiangular and equilateral. Equiangular means having the same angle, and equilateral having the same sides. For example, a square has sides of equal length and angles of equal measure. Therefore, it is a regular polygon. Hence, it is a regular polygon. A rectangle is equiangular but not equilateral. Is a rectangle a rough regular polygon? No. Is an equilateral triangle a regular polygon? It is. It is a regular polygon. It is also a regular polygon because its sides are same and angles are also same, right? Here in this case, 1, 2, 3, 4, all the angles are same and all the sides are also same. Therefore, it is a regular polygons. Here you see, all the sides are same and all the angles are same. Therefore, it is also a regular polygons. Here you see, here all the angles are not same, right? Therefore, polygons that are not regular, these are not regular polygons. Ease of sign double bar and one bar indicate segments of equal length. In the previous classes, have you come across any quadrilateral that is equilateral but not equiangular? Recall the quadrilateral shapes you saw in earlier classes: rectangle, square, rhombus, etc. Is there a triangle that is equilateral but not equiangular? No, it cannot be possible. Now, angle sum property. Do you remember the angle sum property of a triangle? The sum of the measures of the three angles of a triangle is always 180 degree. Recall the methods by which we tried to visualize this fact. We want to extend the idea to a quadrilateral? Here, see, this is a quadrilateral A, B, C, D, right? If we draw it diagonal, that is A and C, we get two triangles. This is A, B, C and A, D, C, right? We know that in a triangle, the sum of the angles of the measures is 180 degree. Therefore, here in this case also, you see, there are two triangles. For this triangle, the sum is 180 degree, and for this triangle the sum is 180 degree, and for the whole quadrilateral it will be 180 plus 180 degree, 180 degree plus 180 degree, that is the sum is 360 degree. Sum is 360 degree. That means in a quadrilateral, so the sum of the angles of a quadrilateral is always 360 degree. Here I have seen some results also in the same way. Here is a cardboard, and if we put the cardboard in this way, that is, we'll get in the interior of the all the interior angles, the angle 1 plus angle 2 plus angle 3 plus angle 4, and this is always 360 degree, right? You see, this is 360. That means the sum of the angles of a quadrilateral is always 360 degree, right? Here also, in this case also, you see that the angle x plus angle y plus angle z plus angle w is also 360 degree, right? That means these quadrilaterals were convex. What would happen if the quadrilateral is not convex? Consider quadrilateral ABCD is split into two triangles and we find the sum of the interior angles. If we split this one, here see, if we split this one, here you see, this is a quadrilateral, and if we split this one into two triangles, suppose this one, right? Therefore, there are two triangles 1 and 2. The sum of this triangle is 180 degree. The sum of these three angles is 180 degree, and therefore the sum of the two triangles is 180 degree plus 180 degree, and that is 360 degree. 360 degree. That is, we know that in case of quadrilateral, that means if it has four sides, the sum of the angles of the four angles is always 360 degree, whether it is a convex polygon or concave polygon. In all the cases, the sum of the angles of the quadrilateral is always 360 degree. Dear friends, if you like this video, please subscribe, like and share. Thank you everybody for watching this video.